Hello everyone, this is the video on JEST PYQs of quantum mechanics. Okay, so we'll be solving the JEST PYQs from quantum mechanics here in this video. Okay, so let's do. And then the first question is from JEST 2012. Consider the Bohr model of the hydrogen atom. If alpha is the fine structure constant, alpha is the fine structure constant, the velocity of the electron the velocity of the electron in its lowest orbit is. This is the Bohr model of the hydrogen atom. If alpha is the fine structure constant, velocity of the electron in its lowest orbit is c by 1 plus alpha, c by 1 plus alpha square. Okay. Option C, alpha squared c. Option D, alpha just 1000 times question. Consider the Bohr model of the hydrogen atom. If alpha is the fine structure constant, velocity of the electron in its lowest orbit. Try the question for 2 minutes. Do you remember the fine structure constant formula? Alpha. Then only you can solve it. E square by 4 pi epsilon naught squared c. That is your alpha. Okay. We know MVR is equal to NH by 2 pi, right? Angular momentum is integral multiple of h by 2 pi in Bohr's theory, Bohr's postulate. Okay. Now, as the electron is moving around the nucleus, this is the radius r. So the force, centripetal force, is the equal to what? Electrostatic force, right? ZE square ZE into E. ZE is the ZE is what? The charge of the nucleus and E by R square. Okay. So what is R from here? R are cancelled. Now R comes to this side. MV square goes to that side. So ZE square 1 by 4 epsilon naught. ZE square by MV square. ZE square by MV square. Yeah. Yeah. So this is your R. This is your R. Now what will I do? I will put this R here. Okay, MVR is equal to NH cut. So MVR is equal to NH cut. So MV into R is this much 1 by 4 pi epsilon naught ZE square divided by MV square is equal to NH cut. So cancelled. This is V goes to that side, ZE square, NH comes to this side, NH cut 1 by 4 pi epsilon naught, what V. So this is V. If you see the dependence also, V is proportional to Z by M, which we know this. But see here, this is V expression for V at which orbit? At nth orbit. Okay. Now the question is what? The velocity of the electron in its lowest orbit. Lowest orbit means ground state. That means n is equal to 1. So for lowest orbit, n is equal to 1. So V will be how much? Just put 1 here. 1 by 4 pi epsilon naught. ZE square divided by h cut. Now if you see, alpha is what? E square by 4 pi epsilon naught h cut c. Okay, this is a hydrogen atom. Hydrogen atom Z is equal to 1. So I can put Z is equal to 1 by 4 pi epsilon naught. E square by h square. What is alpha? Alpha is E square by 4 pi h square 4 pi epsilon naught h square c. So what will I do here? See, I will multiply c, divide a c. Okay, so that I will get this term E square by 1 by 4 pi epsilon sc. Okay, this is alpha. So I can simply write it what? Alpha c. Okay, so alpha is equal to what? B by c. Okay, so here, got it. This is clear. So option D is the answer. Option D is the answer. Next question, question number 2. Yeah. Sigma x is equal to f dagger plus f. Sigma y is equal to minus I f dagger minus f, where sigma dash are Pauli spin matrices. Pauli spin matrices, and f dagger obey anti-commutation relations f is equal to 0, f dagger is equal to 1. Okay. Then question is sigma z is how much? Sigma z is given by sigma z is given by f dagger f minus 1 to f dagger f minus 1 to f dagger f plus 1 f dagger f. So I have this question came in just 2012. This easy question. Okay. Sigma x, sigma y given. That's right. Sigma x is given f dagger plus f sigma y given. Is it right? We have an anti-commutation relations. F is equal to 0. F if dagger is equal to 1. That means what anti-commutation? This is anti-commutation bracket. So f dagger plus f dagger f it will be 1. Okay, this is the meaning of it. There should be a plus sign here. Okay, if commutation means suppose commutation AB, that means AB minus BA, but here this is this bracket, curly bracket. So AB plus BA, anti-commutation. Okay. So sigma x sigma. We know sigma x into sigma y is equal to how much? Pauli matrices I sigma z. I sigma z. We are asked sigma z. So let's take sigma z to left side. I sigma z is equal to sigma x into sigma y. Sigma z is equal to 1 by I sigma x sigma y. So 1 by I sigma x is this much. F dagger plus f. Sigma y is minus I into f dagger minus f. So this goes to this side. Minus I by I goes outside. F dagger plus f. Um, uh, F dagger minus f. Alright. So this becomes minus 1. F dagger square minus f dagger f plus f dagger minus f square. Okay, minus f square. Now f is 0. That means what f plus f is 0. This 2f square is 0. So f square is 0. Okay, from here. F square is 0. So this becomes 0. Okay, this becomes 0. So it will be minus f dagger square. Okay, now we had done if dagger is equal f dagger plus f dagger f is equal to 1. So can I write if dagger is equal to 1 minus f dagger f, isn't it? 1 minus f dagger f. Yeah. So f dagger. So okay, this one is this plus 1 minus f dagger f. Yeah. Replace this one. 1 minus f dagger f. I put it. Alright. Now this one is also 0. Okay. This one is also 0. So minus f dagger f plus 1 minus f dagger f. The answer will be minus of 1. If you see minus 2 f dagger f. 1 minus 2 f dagger f. So if I open the bracket, it will be 2 f dagger f minus 1. So that will be the answer. Okay. That will be your answer. Okay. So this is question number 2. So question number 3. Consider a system of two spinor particles with total spin S is equal to S1 plus S2, where S1 and S2 are in terms of Pauli matrices. Sigma I. The spin triplet projection operator. Spin triplet projection operator is consists a system of two spinor particles with total spin S is equal to S1 plus S2, and in terms of Pauli spin matrices sigma I. The spin triplet projection operator is options are 1 by 4 plus S1 dot S2, 3 by 4 minus S1 dot S2, 3 by 4 plus S1 dot S2. Option D, 1 by 4 minus S1 dot S2. So also came in JEST 2012. Spin triplet projection operator. Spin triplet. When it is a triplet, if S is equal to 0, then multiplicity 2S plus 1 is equal to what? 2 into 0 plus 1, that is 1. So this is a singlet state. Yeah, alright. But when S is equal to 1, the multiplicity 2S plus 1 becomes 2 into 1 plus 1, that is 3. This is which state? This is a triplet state. Okay, so this is what we want. We need to put S is equal to 1, then we will get the spin triplet projection operator. Now S is given as S1 plus S2. Okay, so S square will be S1 square plus S2 square plus 2S1 dot S2. Yeah, right. So S1 square is how much? S1 whole into S1 plus 1 h cut square. S2 square is S2 whole into S2 plus 1 h cut square. So if I put now spin of electron is, these are two electrons. Spin of electron is half. S1 is half. S2 is half. So just put it here. Half whole into half plus 1 h cut square is equal to 3 by 4 h cut square. This one is also 3 by 4 h cut square. So just have to put it here. Okay. So S square is equal to what? S square is equal to S1 square plus S2 square plus 2 S1 S2 S1 S2. So 3 by 4 h cut square, 3 by 4 h cut square plus 2 S1 dot S2. Yeah, is that alright? So this becomes what? 3 by 2 h cut square plus 2 S1 dot S2. S square. Okay, now for spin triplet, S is equal to 1. Okay, so this S square is S equal to S plus 1 over H cut square is equal to 3 by 2 H cut square plus S1 dot S2. So 1 into 1 plus 1 H cut square is equal to 3 by 2 H cut square plus S1 S2. So this is 2 H cut square is equal to 3 by 2 H cut square plus S1 dot S2. Yeah, but the spin triplet projection operator, how will I write it? I'll just see H cut square, let's take it as 1. It's considered 1 sometimes. So spin projection operator is this one. Okay, this one is equal to this. Don't like subtract it or anything. This is a spin projector operator. Suppose I something. It'll be what? 3 by 2 H 3 by 2 plus S1 dot S2. If I take 2 common, 3 by 4 plus what? So this was 2 here. 2 was there. I missed 2 here. 2. So if I take 2 common, this will be, yeah. If you see which option is it, see this one. We need the inner one, like inside part. That is the projection operator. 3 by 4 plus S1 dot S2. Alright, clear? It's a bit different. Same kind of thing, but it's a bit like a bit different. So question number 3 on. Question number 4. Consider a spin half particle in the homogeneous magnetic field. In the homogeneous magnetic field of magnitude B along z-axis, which is which is prepared initially, which is prepared initially in a state psi is equal to 1 by root 2 1 by root 2 plus spin up plus spin down at time t is equal to 0. At time t is equal to 0. At what time t? At what time t will the particles be? Will the particles be in the state? Be in the state minus a psi. Okay. Your mu b is the Bohr magneton. Consider a spin-up particle in the homogeneous magnetic field of magnitude b along z-axis, which is prepared initially in a state this. Time t is equal to 0. At what time t will the particle be in the state minus psi? Okay, try this question. Thus, a spinor particle in the homogeneous magnetic field of magnitude b along z axis, which is prepared initially in a state this at time t0. At what time t will the particle be in the state minus psi? Hmm. So this state, see this state, I have to write it as 1 by root 2 1 1. Okay. So what time t will the particle be in the state minus psi? So psi xt by what? 1 by root 2 1 1 e to the power minus I e t by h cut. You know it, right? Hmm. Which is actually it's saying what? Minus psi. It's saying that it should be minus psi. So how? So minus psi means what? We just put this side and become minus of 1 by root 2 1 1 e to the power minus I e t by h cut is equal to minus 1 by root 2 1 1. Okay. Now see, E is what? E is a minus mu dot B. Okay, minus mu dot B. We know this mu B dot B. This is your Bohr magneton. This is your magnetic field. So I can put here 1 by root 2 1, and this will be cancelled out. So e to the minus I minus I mu B B T by h cut. Okay, and sorry is equal to minus 1. Okay, now minus 1 is how much? E to the power minus I mu b e by h cut is equal to e to the power I pi. We can say that e to the power I pi is cos pi plus I sin pi. I sin pi is 0. So this is minus 1. Okay, so minus 1. So I can just compare these two. I will get it as mu b b t h by h cut is equal to pi. Okay, so how much is t? Time is pi h cut by mu b. That is the answer. Okay, clear? Alright, that's the answer. Okay, I didn't write the options, it's alright. I hope you understood. We just have to write the wave function in the time t, that is minus psi, and just do the solution. Okay? Yeah. So this was a question number 4. So question number 5. The ground state energy of 5 identical spinor particles, 5 identical spinor particles which are subject to which are subject to a one-dimensional simple harmonic oscillator, simple harmonic oscillator, oscillator potential of frequency omega is the ground state energy of 5 identical spinor particles which are subject to a one dimension simple harmonic oscillator potential of frequency omega is a 15 by 2 h cut omega, b 13 by 2 h cut omega, c 1 by 2 h cut omega, and d 5 h cut omega. Okay. Ground state energy of 5 identical spinor particles which are subject to a one-dimensional simple harmonic oscillator potential of frequency omega is. Try this question in a few minutes. Okay, see, five identical spin half particles. Spin is half. So suppose five particles. So suppose this is a harmonic oscillator potential. These are the levels. So in one level, how many particle can be there? As it is spin half particles, so the multiplicity is what? 2s plus 1. That is 2 into 1 plus 1. 2 into 1 by 2 plus 1. That is 2. So in one state, only two particles can be there. So total 5. That means you can arrange this like this: 2 here, and 1 here only. Total 5. So the ground state energy of 1D harmonic oscillator is what? Half h cut omega. So this is two particles, 2 into half h cut omega. This is 2 into 3 by 2 h cut omega. And there is only 1 here. So next state is 5 by 2. So 5 by 2 h cut omega. So if we just add them, so total energy will be what? Total energy will be what? 2 into half h cut omega plus 2 into 3 by 2 h cut omega plus 1 into 5 by 2 h cut omega. That is, if you see, h cut omega plus 3 h cut omega plus this is 2.5 h cut omega. So this is 6.5 h cut omega. Okay, 6.5 can be written as 13 by 2 h cut omega. Okay, let's see the options. Yeah, 13 by 2 h cut omega. Is it clear? Easy question. Okay. Suppose the same question, if it was given like 5 spin 3 by 2 particles. Suppose the same question, 5 spin, 5 identical spin 3 by 2 particles are arranged in a 1D harmonic oscillator. So what would I have done? 3 by 2. That means multiplicity 2s plus 1 is equal to 2 into 3 by 2 plus 1. That is 4. So in one state, 4 particles can be there. So how many is left in the second state? 1 only. So 4 into half h cut omega plus 1 into 3 by 2 h cut omega. This much only, right? That will be 2 h cut omega plus 1.5 h cut omega. That is 3.5 h cut omega. Is it clear? Yeah. This is how to solve this type of questions. Okay, next question. Question number 6. The spatial part of a two electron state is symmetric under exchange, symmetric under exchange if upspin and downspin represent spin up and spin down spin down states respectively, respectively of each particle. The spin part of the two particle state, the two particle state is okay. The spatial part of A is option A up down, option B down up, option C down up minus up down whole divided by root 2, option D down up up down whole divided by root 2. Yeah, try this question. Still doing JEST 2012 questions. Okay, so you can see how many questions came in 1 year of quantum mechanics questions come a lot in the JEST exam. Try this question. Spatial part of a two electron state is symmetric on the exchange. If spin up, spin down are there, spin part of the two particle state is spin part of it. Okay, let me do it. The spatial part is symmetric. See, psi should be what? Psi spatial, psi spin. So here, this is a these are electrons, two electron states. Electrons are what? Are they boson or fermion? Electrons are fermions. So fermions have the total wave function as antisymmetric. Okay, the total wave function of the fermion should be antisymmetric. And in the question it is written psi spatial is symmetric under exchange. So psi spatial is symmetric. So psi spin should be what? It should be antisymmetric to make the whole thing antisymmetric. So this should be antisymmetric. Okay. So psi spin should be spin part of the two particle state should be antisymmetric. So from here, can you see which one is antisymmetric? Antisymmetric. See this is not. This is just one. This is not antisymmetric. This is not antisymmetric. This is symmetric because there is a plus sign. When there is a plus sign, if we exchange it, it will be the same thing. I mean, for example, AB plus BA. If we change the order, it will be the same thing, isn't it? Right? But suppose AB minus BA, right? If we change the order, it won't be same. So like this is what? This is your anti-symmetric. Okay, that means AB minus BA. Like if I change the order, it won't be same. So anti-symmetric. So which one is this? Option C. Okay, option C will be your anti-symmetric wave function. So this should be your answer. As this is fermion, the total wave function should be anti-symmetric. Yeah. It was your question number 6. Now question number 7. Question number 7. The wave function of a free particle in one dimension is given by psi x is equal to a sin x plus b sin 3x. The psi x is an eigenstate of is an eigenstate of dash. Option A position operator. Option A position operator. Option B the Hamiltonian. Option B the Hamiltonian. Option C the momentum operator. The momentum operator. Option D the parity operator. The parity operator. The wave function of a free particle in one dimension is given by psi x is equal to a sin x plus b sin 3x. Okay. So the psi x is an eigenstate of dash position operator, Hamiltonian operator, the momentum operator, and the parity operator. This question. This is also JEST 2012. It's still going. JEST 2012 is still going. And these are very good questions. See, free particle one dimension is given by psi x is equal to a sin x plus b sin 3x. The psi x is an eigenstate of dash. Okay. If I put minus x, what will happen? A sin minus x plus b sin 3 minus x. So it will be what? Minus a sin x minus b sin 3x. So minus of a sin x plus b sin 3x I am getting, isn't it? So I am getting psi minus x is equal to what? Minus of psi x. So this is which kind of function? This is your what? Odd function. Odd function. So odd function negative parity. So I am getting negative parity. That means it's called what? Parity operator. This is your parity operator. Okay. Psi minus x is equal to psi x. Suppose this is your even parity. But psi minus x is equal to minus sin x. This is your odd parity. Okay. So here it is odd parity. So this is your parity. So parity operator. Yeah. Parity operator. I hope you're clear with this. It's question number 7. Question number 8. Question number 8. The quantum state, the quantum state sin x of spin plus exponential I phi cos x downspin, where where up down is equal to 0 and x phi are real, is orthogonal to option A sin x upspin, option B cos x upspin plus exponential I phi sin x downspin, option C minus cos x upspin minus exponential I phi sin x downspin, option D minus exponential minus I phi cos x upspin plus sin x downspin. Yeah, that's the question. Try this question. It's a very good question again. Please try. Quantum is sin x upspin exponential I phi cos x downspin. Tell me, this is your what? What is given? This is what is given here. And tell me. Hmm? This is ket vector. It's written like this, right? This is ket. So ket vector I can say ket psi. Ket psi can be written as sin x up, then plus exponential I phi cos x down. This is ket vector. I can write the bra vector of this. So bra vector as sin x, okay, up like this. This should be conjugate because like bra and ket vector are conjugate of each other, complex conjugate of each other. So minus exponential, sorry, no, ex- plus exponential minus I phi cos x bra down. Yeah. So now what? Now what is given in the question? They are orthogonal 0. So I will just multiply them. Right, right. So did I do a mistake? Okay, this one will be down. This one will be down. This one will be up in this case. Okay, yeah, now it's correct. Okay, now this one will be multiplied with this one. This up, up. So exponential I phi cos x sin x up, up plus um, exponential I phi sin x cos x down, down. Hmm. Okay, wait, this is wrong. No, 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 no. The question is what? Let me read the question again. The quantum state this is orthogonal to which of the options? So we have to check one option. Yeah, that's the way to do it. I was myself confused like how to do it. Okay, no problem. Let's write this. Suppose this is your psi. Let's write it in. Let's. It's okay. It's okay. Mistakes happen. Psi is equal to sin x up plus exponential I phi cos x down. So which I will multiply, which upon option I will multiply with psi, that it will come 0. Let's check one. See, this is not a chance. This is not a chance. I will not get 0 from here. Let's check this one. Even this one, I don't think. What is given? That one. Option B. Cos x up exponential I sin phi. Cos x up exponential I phi sin x down. Do you think they both will, if I multiply them, they will be 0? See, this is sin x cos x. Up is 1 plus this is exponential 2I phi sin x cos x. So this is not giving me 0. So this is also not the answer. Option C. Let's check this one. Minus cos x up minus exponential I sin. Okay. So minus cos x up minus exponential I phi sin x down. What is our kate vector? Sin x up plus exponential I phi cos x down. So if I take the inner product, bracket is equal to this is minus sin x into cos x. This is 1. This is minus exponential again 2I phi sin x into cos. No, this is also not 0. So one option is left. Let's check it anyway. Minus exponential minus I phi cos x. Okay. So minus exponential minus I phi cos x up plus sin x down. Next term. So let's check this one. Okay. So psi will be, it was sin x. Our first term was sin x. So minus exponential minus I phi cos x plus this one was your exponential I phi cos x into the sin x. Yeah. See, these two are opposite, like completely. And another one thing. See, this is given in kit. See, this is given in kit. So its bra will be what? Its bra will be minus exponential I phi, right? I phi cos x. This is so this one will become I phi. Okay, got it. So and this can be now cancelled out. See, all right. Is it all right? I hope you understood. Okay, write another question. So your question number 8. Question number 9.
particle of mass m. Okay, like it's in the walls. X is equal to minus L by 2 to x is equal to L by 2, infinite 1D, infinite well. Let me write it in shortcut. It's a long question. Infinite. Particle is in the ground state. Phi naught x is equal to root over of 2 by L cos pi x by L. Okay. The walls of the box, the walls of the box are suddenly moved to form a box extending from a box extending from x is equal to minus L to x is equal to L. Yeah, x is equal to L. What's the probability that what's the probability that what is the probability that the particle will be in the ground state in the ground state after this sudden expansion after this sudden expansion. Okay, option A 8 by 3 pi whole square, option B 0, option C 16 by 3 pi whole square, option D 4 by 3 pi whole square. This question came in just 2013, and this is a homework. Okay, I'll solve it anyway in the next class, but just try this once. Okay. The walls of the box are suddenly moved to form a box containing x is equal to minus L to x is equal to L. What's the probability that particle will be in the ground state after this sudden expansion? Okay. So that will be it for this class. Okay. It's only 1 year we could discuss today. We'll be discussing more questions in the next sessions. Okay. Thank you very much for watching. Keep tuned to the channel. Thank you.